Reality is built on frameworks we cannot see. The universe is not an empty stage, but a living tapestry of invisible forces and patterns. Physicist John Wheeler once captured this beautifully, noting that spacetime directs matter, and matter shapes spacetime in return. This video will reveal 25 of these hidden cosmic structures, from dark matter webs to quantum fields, and by the end, you will see the fundamental architecture of existence in a completely new light. What if the vacuum of space is actually a frothing sea of energy? And what kind of geometric shapes are curled up in dimensions beyond our own? How does the idea of a hidden cosmic order change your sense of place in the cosmos? Galaxies do not drift through the cosmos in isolation. They are drawn together, pulled into immense clusters and sprawling superclusters by the deepest gravitational wells in the universe. Think of these wells as colossal valleys carved into the fabric of spacetime itself by the sheer concentration of mass, most of it the invisible dark matter of the cosmic web. A galaxy falling into one of these basins is like a marble rolling down a steep, smooth hillside, gaining speed as it descends into a dense metropolis of stars. These gravitational anchors are what prevent our entire local group of galaxies from flying apart, holding us in a mutual dance that will eventually draw the Andromeda Galaxy and our own Milky Way together in a distant future merger. The shape and depth of these wells dictate the fate of everything within them, orchestrating a slow, cosmic choreography over billions of years. But what creates these profound dips in spacetime in the first place? The answer lies with the universe's most elusive architects. These profound dips in spacetime are not just valleys, they are the very signature of mass. Envision the universe not as a rigid stage, but as a vast, flexible sheet, a fabric that can stretch and warp. When you place a heavy object, like a star or a black hole, onto this sheet, it creates a deep indentation, a gravitational well. This is the core of Einstein's revolutionary idea, his general theory of relativity. He redefined gravity itself, showing it is not some mysterious force pulling at a distance, but rather the natural result of mass curving the geometry of spacetime around it. In his own powerful words, matter tells spacetime how to curve, and spacetime tells matter how to move. Think of our moon orbiting the Earth. It is not being pulled by an invisible string. It is simply following the curved path, the groove, that Earth's mass has created in the cosmic fabric, like a marble rolling around a funnel. This curvature has breathtaking consequences. It bends the very path of light, a phenomenon we call gravitational lensing, where distant galaxies appear as stretched arcs around a closer massive object. It even dictates the flow of time. A clock ticks just a little slower when it is deep within a powerful gravitational well, like near a black hole, compared to a clock out in the emptiness of space. This hidden geometry of curved spacetime orchestrates every major motion in the cosmos, from a planet's steady orbit to the intricate dance of binary stars. It reveals that the universe operates according to an invisible topographical map, one of hills and valleys sculpted by mass. But if this is the large-scale structure of reality, what is happening at the smallest scales in the seemingly empty vacuum? What other geometric patterns are woven into the fabric of space itself? Yet this smooth cosmic fabric conceals a deeper, more chaotic truth. At the very smallest scales imaginable, the universe is not a placid sheet but a turbulent, frothing sea. This is the realm of quantum foam, a concept from physicist John Wheeler describing the very texture of spacetime at the Planck length, a scale so incredibly tiny it defies everyday comprehension. Here, the orderly geometry of general relativity breaks down completely. Spacetime itself becomes a chaotic foam, a seething ocean where virtual particles and energy fluctuations borrow from the future to pop into existence for the briefest of moments before vanishing again. It is a landscape of transient wormholes and fleeting distortions, a constant bubbling activity at the foundation of everything. This means the vacuum of space is not truly empty. It is a dynamic, energetic medium, more like an ocean with waves constantly crashing on a shore we cannot see. This hidden, frothing structure underpins all of reality, influencing how particles interact and potentially even shaping the fundamental constants of nature. It challenges our most basic notions of a static, predictable universe, suggesting instead a vibrant and active foundation at the heart of all existence. But how does this chaotic, microscopic activity give rise to the stable, pervasive fields that fill the cosmos and grant particles their mass? This question leads us directly to one of the most famous and most misunderstood structures in all of physics. This universal sculptor of substance, the Higgs field, permeates all of space like an invisible, treacle-like medium. Its existence was a monumental prediction, finally confirmed in 2012 by experiments at the Large Hadron Collider at CERN. The discovery of the Higgs boson particle served as definitive proof that this field is real. Physicist Peter Higgs himself noted that this hidden structure explains how two fundamental forces of nature, the weak nuclear force and the electromagnetic force, unify into a single electroweak force at extremely high energies. So how does it work? Think of the universe as filled with an unseen cosmic molasses. Fundamental particles moving through this molasses experience a kind of resistance, a drag that we interpret as their mass. Particles like the quarks that make up protons and neutrons interact strongly with this field and thus acquire significant mass. Other particles, like the photons that carry light, simply do not interact with it at all, which is why they zip through the cosmos at the ultimate speed limit, the speed of light. Without this pervasive field, nothing would have mass. Electrons would not be captured by atomic nuclei, atoms could never form, and the complex structures of planets and life would be impossible. The very substance of our reality, the stuff that makes you, me, and the stars themselves, owes its tangibility to this one hidden cosmic field. It is the ultimate source of mass in the universe. But if this field gives matter its substance, what other invisible fields orchestrate the fundamental forces we experience every day? Yet another cosmic field operates on an even more intimate scale, binding the very heart of matter together. While the electromagnetic field governs the world of atoms and light, a far more powerful force field is at work within the atomic nucleus itself. This is the strong nuclear force field, the mightiest fundamental force in the universe. It acts as nature's ultimate superglue, overcoming the fierce repulsion between positively charged protons and binding them together with neutrons to form the nuclei of every atom that exists. Without this hidden structure, every atomic nucleus would instantly fly apart, and the universe would be nothing but a diffuse cloud of hydrogen, unable to form the heavier elements essential for planets and life. Its force carriers are particles called gluons, and their name is wonderfully descriptive, as they literally glue quarks together to form protons and neutrons. The strength of this field is almost unimaginable, confined to a vanishingly small domain only about 1/millionth of a billionth of a meter across. It is this intense, localized power that forges the elements in the cores of stars and during supernova explosions, scattering the building blocks of complexity throughout the cosmos. The stability of the very atoms that make up your body is a direct gift from this profound and deeply hidden force field. But if one force holds the nucleus together, another governs its transformation, orchestrating the slow decay that powers the Earth's core and allows for radioactive dating. While the strong force binds the atomic nucleus with immense power, another, more subtle force field works to transform it from within. This is the weak nuclear force field, a fundamental but elusive player in the cosmic drama. It operates on an even smaller scale than the strong force and is responsible for a crucial process known as radioactive decay. Think of it as the universe's alchemist, quietly changing one type of subatomic particle into another. For instance, inside the Sun, the weak force is essential for the first step of nuclear fusion, allowing two protons to overcome their mutual repulsion and stick together, beginning the chain reaction that bathes our solar system in light and warmth. It is the reason the Sun shines. On Earth, this same force governs the natural decay of unstable elements, the heat deep within our planet, which drives volcanoes and tectonic shifts, is largely generated by the weak nuclear force slowly transforming heavy elements in the Earth's core. This hidden field is also the key to radiocarbon dating, as it carefully changes nitrogen in our atmosphere into a special form of carbon that archaeologists use to peer back in time. Without this quiet, transformative force, the elements would be frozen in their original states, unable to change or release the stored energy that makes a dynamic, living universe possible. It provides a necessary counterbalance to the strong force's rigid grip, allowing for the slow, steady transmutation that fuels both stars and scientific discovery. But if these fields govern the tiny quantum world, what invisible structure orchestrates the vast, orderly patterns of the cosmos on the very largest scales? This transformative power of the weak force, however, is not an isolated phenomenon. Deep within the cores of stars, under conditions of unimaginable heat and pressure, a remarkable unification occurs. The electromagnetic force and the weak nuclear force, which appear as entirely separate entities in our everyday world, merge into a single, fundamental power, the electroweak force. This is the first step on a theoretical ladder leading to a grand unified theory, a single mathematical framework that would describe all fundamental forces as different manifestations of one primordial superforce. Physicists propose that in the first fleeting moments after the Big Bang, the entire universe was energetic enough for this perfect symmetry to exist. There was no distinction between the force that governs radioactive decay and the force that binds atoms into molecules. As the cosmos expanded and cooled, this unified force underwent a phase transition, much like steam condensing into water, breaking apart into the distinct forces we recognize today. The quest for a grand unified theory is a search for this lost symmetry, a hidden structure of mathematical elegance that once orchestrated all of cosmic creation. It aims to weave the strong nuclear force into this same tapestry, revealing a deeper, more profound order underlying the seemingly separate rules of reality. But if such a unification governs the quantum world, what hidden structure dictates the ultimate fate of the cosmos itself on the very largest scale? This drive toward unification reveals a profound cosmic narrative, a story of symmetry lost. The universe was not always a place of separate forces. In its first searing moments, a perfect unity reigned. The electromagnetic force, the weak nuclear force, and the strong nuclear force were not distinct entities but were fused into a single, sublime force field. This is the majestic vision of grand unification theories, or GUTs for short. They propose that the fundamental rules we observe are merely fragments of a primordial symmetry that fractured as the cosmos expanded and cooled. Picture a vast, hot ocean of pure energy. As this ocean cools, ice begins to form, but it does not form as a smooth sheet. Instead, it crystallizes into a multitude of intricate, branching patterns. In a similar way, the single unified force of the early universe underwent a phase transition, crystallizing into the distinct forces that now govern our reality. Physicist Abdus Salam, who helped unite the electromagnetic and weak forces, dreamed of this deeper harmony, envisioning an epoch when the forces of nature were one. This hidden structure of a broken symmetry is not just a beautiful idea, it makes tangible predictions. It suggests that the proton, long thought to be stable, might eventually decay, transforming its matter into energy over incomprehensible spans of time. It also points to the possible existence of magnetic monopoles, isolated north or south magnetic poles that would be relics from that first, unified state. Most compellingly, this framework might finally explain one of the universe's greatest mysteries, why there is so much more matter than antimatter. The slight breaking of that perfect initial symmetry could have tipped the scales, allowing the world we know to form from the ashes of mutual annihilation. This quest for a grand unified theory is a search for the universe's original, elegant blueprint, a hidden architecture of breathtaking simplicity underlying the dazzling diversity we see today. But this principle of symmetry extends far beyond the unification of forces, governing the very fabric of motion and time itself. This deep drive toward unification rests upon a bedrock principle, a hidden structure that guarantees the laws of physics are the same for everyone, everywhere. The universe operates on a rule of absolute consistency known as Lorentz symmetry. It means that no matter how fast you are moving, whether you are standing still on Earth or racing through a distant galaxy in a spaceship, the fundamental laws of nature remain identical, and the speed of light in a vacuum is an unbreakable constant. This principle, named for physicist Hendrik Lorentz and forming the core of Einstein's special relativity, is not just a curious fact, it is a fundamental feature woven into the geometry of spacetime itself. To preserve this cosmic rulebook for all observers, the universe performs a subtle, automatic adjustment. Time itself dilates, slowing down for an object in motion relative to a stationary observer, while lengths in the direction of travel contract. These are not illusions, they are real, measurable effects that ensure a beam of light always travels at the same speed, regardless of who is measuring it or how fast they are going. This hidden symmetry is what allows particle accelerators to work, smashing particles together at near light speed to reveal the secrets of matter. It is also essential for the GPS technology in your phone, as the satellites orbiting Earth experience time slightly faster than receivers on the ground, a tiny difference that must be corrected for pinpoint accuracy. This profound invariance fosters a cosmos of reliable order, where fundamental principles are universally trustworthy. Yet, physicists now wonder if this perfect symmetry might break down at the most extreme scales, in the realm of quantum gravity. Theories like loop quantum gravity suggest that spacetime may have a discrete, granular structure at the tiniest possible level, a pixelated reality where our smooth, continuous laws, including Lorentz symmetry, might finally falter. This granular, pixelated view of reality fundamentally rewrites our understanding of space and time. The smooth, continuous fabric of Einstein's universe gives way to a structure of breathtaking intricacy at the smallest possible scales, a fabric woven from one-dimensional loops. This is the vision of loop quantum gravity, a theory proposing that spacetime itself is not a smooth continuum but a dynamic, evolving network. Think of it as the universe's most fundamental fabric, a cosmic chainmail made not of iron rings, but of tiny, vibrating loops of space. These loops, existing at the minuscule Planck length, weave together to form the geometry of the cosmos. In this framework, properties we take for granted, like area and volume, are not continuous. They are quantized, meaning they can only exist in specific, discrete amounts, much like the energy levels of an atom. You cannot have half a unit of area, just as an electron cannot exist in half an energy level. This atomic nature of space and time has profound consequences. It suggests that the terrifying singularities predicted by general relativity, the points of infinite density at the heart of black holes and the beginning of the Big Bang, are not real. There is a smallest possible scale, a finest grain to reality, preventing such infinities from ever forming. Instead of a Big Bang singularity, loop quantum gravity points to a big bounce, a cosmic rebound from a previous phase of the universe. The theory describes this evolving geometry using spin networks, intricate mathematical diagrams where the links and nodes represent the quantized units of space itself. This hidden, woven structure offers a compelling path to a theory of quantum gravity, finally bridging the vast conceptual gap between the cosmic and the quantum. But if space itself is a woven tapestry of information, could it be that this information is all that truly exists, projected from a distant, two-dimensional surface? This radical idea suggests that our seemingly solid three-dimensional universe might be a projection from a distant, two-dimensional surface. Known as the holographic principle, this concept emerged from a deep puzzle in black hole physics. When matter falls into a black hole, what happens to the information it contains? According to the classical laws of physics, that information would be lost forever, a paradox that threatened the very foundations of quantum mechanics. But physicist Leonard Susskind and others proposed a breathtaking solution. They argued that all the information describing everything that falls into a black hole is not destroyed, but is instead perfectly encoded on the black hole's event horizon, its two-dimensional boundary. The three-dimensional interior, with all its apparent substance, is a holographic illusion built from that data. The stunning implication is that this principle might apply to the entire cosmos. Our reality, with its galaxies, stars, and people, could be a vast hologram with the true fundamental degrees of freedom living on a remote bounding surface. Think of watching a breathtaking three-dimensional movie. The entire immersive experience, every detail of depth and motion, is encoded on the flat, two-dimensional surface of the film. In a similar way, the holographic principle posits that our complex universe is a projection from a cosmic film reel stored at the edge of space. This transforms our understanding of reality, suggesting that space itself is not fundamental but emerges from a network of quantum information. It is as if the cosmos operates like an ultimate cosmic hard drive, with all the data needed to describe every particle and force stored on its two-dimensional shell. This hidden structure of information encoding reshapes our concepts of gravity, entropy, and the very nature of existence, proposing that the richness of our world is a magnificent illusion. If the universe is such a grand projection, what other topological marvels could be woven into its hidden geometry? These theoretical tunnels through space-time reveal a geometry far stranger than we can directly see. Wormholes, often called Einstein-Rosen bridges, are hidden structures within the equations of general relativity, first explored by Albert Einstein and Nathan Rosen. They act as cosmic shortcuts, theoretical passages that could connect two incredibly distant points in the universe, or perhaps even bridge entirely separate universes. The mathematics suggests that the intense gravity of a black hole could warp spacetime so severely that it folds back on itself, creating a bridge or a throat to another location. But there is a profound catch. These passages are predicted to be incredibly unstable, snapping shut in an instant, far too quickly for anything to pass through. To hold a wormhole open to make it traversable would require a substance with truly bizarre properties, something known as exotic matter. This is not normal matter, but a hypothetical material that would possess negative energy density, effectively pushing the walls of the wormhole apart against the crushing force of gravity. While we have no evidence that such matter exists or that wormholes are real, their theoretical existence is a powerful reminder of spacetime's dynamic and malleable nature. They show that the cosmos could be threaded with hidden tunnels, a labyrinthine structure woven directly into the gravitational field. This possibility captivates our imagination, suggesting a future of cosmic engineering and interstellar travel that remains, for now, in the realm of profound theory. How do such structures relate to the overall geometry of the universe? Cosmic strings offer another clue to the hidden topography of reality. These frozen cracks in spacetime are relics from the universe's first moments. As the fiery chaos of the Big Bang began to cool, the fundamental forces of nature underwent a series of profound shifts, like water freezing into ice. And just as ice forms with cracks and fissures, the fabric of the cosmos may have solidified with its own imperfections, one-dimensional flaws known as cosmic strings. These are not strings in the everyday sense, but unimaginably dense filaments of pure energy, thinner than a proton yet stretching across vast intergalactic distances. A single inch of cosmic string could weigh more than Mount Everest, warping spacetime around it with its immense gravitational pull. Their existence was predicted by grand unified theories, which suggest they formed when the universe was just a fraction of a second old, as a kind of topological scar tissue from the violent birth of reality. If they exist, these cosmic threads would leave subtle fingerprints on the cosmos, bending the light from distant galaxies into double images and creating faint, telltale ripples in the oldest light we can see, the cosmic microwave background. They would have acted as gravitational seeds, their immense density pulling in the primordial gas that eventually collapsed into the first galaxies and clusters. While we have not yet confirmed their existence, the search for cosmic strings is a hunt for a hidden fossil, a direct remnant from the universe's most explosive moment. This search for relics leads to an even more transformative field, one responsible for the very size and shape of the cosmos we inhabit. This rapid expansion was driven by a hidden engine, a hypothetical field of energy known as the inflaton field. To resolve deep mysteries about our universe's large-scale structure, physicist Alan Guth proposed the theory of cosmic inflation. Why does the cosmos look so remarkably uniform in every direction we look, and why is its overall geometry so incredibly flat? The horizon problem asks how regions of space now billions of light-years apart could ever have communicated to reach the same temperature, given that light has not had enough time to travel between them since the Big Bang. The answer, according to inflation, is that they were once intimately connected in a tiny, subatomic volume before being violently stretched apart. The inflaton field provided a temporary, powerful, repulsive gravity, causing the universe to expand at an exponential rate, far surpassing the speed of light for a fleeting fraction of a second. This is not a violation of relativity, as nothing was moving through space faster than light. Space itself was stretching. This incredible growth spurt ironed out any primordial wrinkles, smoothing the cosmos to the uniformity we observe and flattening its overall geometry. But it did not create a perfect vacuum. Tiny quantum fluctuations in the inflaton field itself were also stretched to astronomical sizes, becoming the faint seeds of density, the gravitational anchors around which all future structure would coalesce. These minute ripples are frozen in time, imprinted as temperature variations in the oldest light we can see, the cosmic microwave background. This afterglow of the Big Bang is a direct snapshot of that inflationary epoch, a celestial blueprint from which galaxies and voids would later emerge. The inflattened field was a transformative, dynamic phase that set the entire cosmic stage. But how did these subtle ripples evolve into the distinct, clustered universe we see today? The answer is written in the echoes of primordial sound waves. These frozen ripples are a cosmic echo of the universe's first sound. In its fiery infancy, the cosmos was a seething, opaque soup of particles and radiation, a dense plasma where light was constantly trapped. Within this hot fluid, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This created a tug of war, generating powerful sound waves that traveled through the primordial medium at over half the speed of light. These were not gentle waves, but immense spherical pressure fronts that rippled outward for hundreds of thousands of years. Then, a pivotal moment arrived. When the universe had cooled enough for stable atoms to form, in an event known as recombination, the fog suddenly cleared. Photons, the particles of light, were finally set free, and that first brilliant flash is what we now detect as the cosmic microwave background. At that precise instant, those vast sound waves were frozen in place, their spherical crests imprinted as a subtle pattern in the distribution of matter. This fossilized ripple is known as a Baryon acoustic oscillation. Today, we can still see its signature. When astronomers map the positions of millions of galaxies, they find that galaxies are slightly more likely to be separated by a specific preferred distance, about 500 million light-years apart. This distance is the radius of that ancient spherical shell, a standard ruler etched into the cosmos. By measuring this ruler at different cosmic epochs, scientists can track how the expansion of the universe has changed over billions of years. It was precisely this kind of measurement that provided some of the most compelling evidence for dark energy, the mysterious force accelerating cosmic expansion. This hidden structure is a direct snapshot of the universe at only 380,000 years old, a relic of its first and only symphony, the vibrations of which ultimately orchestrated the grand architecture of galaxies and voids we see today. But this same primordial flash of light holds another, even more intricate pattern, a detailed blueprint of the early universe's minute imperfections. These subtle temperature ripples in the cosmic microwave background are the universe's oldest fossil, a baby picture from its first 380,000 years. While this afterglow appears almost perfectly smooth to our instruments, it is not uniform. Scattered across the sky are minuscule variations, tiny hot and cold spots differing by only millionths of a degree. This anisotropy, this hidden pattern of imperfection, was first mapped in stunning detail by satellites like COBE and Planck, revealing a cosmic blueprint of breathtaking precision. These temperature differences correspond directly to the density of matter in the early cosmos, the slight gravitational hills and valleys where matter was just a bit more or less crowded. It was within these minute overdensities that the seeds of all future structure were sown, the gravitational anchors that would, over billions of years, pull in gas to form the first stars, the galaxies, and the vast cosmic web we see today. The specific pattern of these spots provides overwhelming evidence for cosmic inflation, as their statistical properties match the prediction that they were born from quantum fluctuations stretched to cosmic size. This means the grand tapestry of galaxies, including our own Milky Way, can trace its origin back to these quantum ripples, tiny probabilistic tremors from the universe's very first instant, now frozen forever in this ancient light. How could such a fundamental connection between the largest cosmic structures and the smallest quantum events exist? the answer may lie in a phenomenon that seems to weave the universe together at its most fundamental level. This spooky action at a distance reveals a universe stitched together with invisible threads. Two particles can become so intimately linked that measuring one instantly determines the state of its partner, even if they are separated by the width of a galaxy. Albert Einstein was deeply troubled by this, famously calling it spooky action at a distance because it seemed to violate the cosmic speed limit set by light. He believed information could not travel faster than light, yet entanglement appeared to do just that. Decades of meticulous experimentation have proven this strange connection is real, with laboratories confirming entangled links over distances of hundreds of kilometers. This phenomenon, known as quantum entanglement, shatters our classical understanding of a local universe where objects are separate and influence requires a signal traveling through space. It suggests instead that the cosmos is woven with a hidden structure of non-local correlations, a fundamental interconnectedness where the idea of a truly isolated particle is an illusion. This deep linkage is not just a theoretical curiosity, it is the bedrock of revolutionary technologies. Quantum computers harness entangled bits or qubits to perform calculations at speeds impossible for classical machines, while quantum cryptography uses these links to create theoretically unbreakable codes. The profound implication is that the fabric of reality includes instantaneous connections that transcend our everyday notions of space, hinting at a holistic, unified quantum web where everything is part of a single, intricate whole. If such pervasive interconnectivity binds the quantum realm, how does it manifest across the vast emptiness of the cosmos? The answer may lie in the very nothingness of space itself. This seeming nothingness between stars and atoms is a cauldron of activity. The quantum vacuum is not an empty stage but a vibrant, energetic medium, a hidden structure of reality known as quantum vacuum energy. Even in the deepest, most perfect void we can imagine, the laws of quantum mechanics dictate that empty space is not truly empty. It seethes with a faint, persistent hum, a sea of transient fluctuations where particle and antiparticle pairs borrow energy from the future to pop into existence for an immeasurably brief moment before annihilating each other and vanishing back into the background. This endless, frothing dance of virtual particles is not just a theoretical curiosity, it has a tangible, observable effect. In the late 1940s, physicist Hendrik Casimir made a stunning prediction. He envisioned two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, just a few millionths of a meter apart. In the vast space outside the plates, a rich spectrum of these virtual particles can flicker in and out of being. But in the narrow gap between the plates, only certain wavelengths of this quantum activity can fit, much like how only specific musical notes can resonate in a pipe of a given length. This limitation means that more virtual particles push on the outside of the plates than on the inside, creating a subtle but measurable pressure that forces the plates together. This is the Casimir effect, a physical force born from the activity of nothingness, and it has been confirmed repeatedly in laboratory experiments. It is direct proof that the vacuum is a dynamic, energetic substrate. Yet this profound discovery leads to one of the greatest puzzles in all of physics, the cosmological constant problem. When physicists attempt to calculate the total energy density of this quantum vacuum, the number they get is astronomically, impossibly large. It suggests a vacuum energy so powerful that it should have ripped the universe apart in its first instant, preventing any stars or galaxies from ever forming. And yet, when we observe the cosmos, we measure a value for dark energy that is 120 orders of magnitude smaller. This is the most severe discrepancy between theory and observation in the history of science, a glaring sign that we are missing something fundamental about the nature of empty space. This bubbling sea of potentiality is the true foundation upon which particles dance and forces act, a hidden structure that influences everything from subatomic interactions to the ultimate fate of the cosmos. Could this enigmatic energy be understood or perhaps even harnessed by looking beyond our familiar three dimensions? Brain theory in string theory suggests the answer is yes. This vision of a cosmic hologram finds a breathtaking extension in the idea that our entire universe might be a single three-dimensional membrane or brain, adrift within a higher dimensional reality. String theory proposes that the fundamental constituents of everything are not point-like particles, but unimaginably tiny, vibrating loops of energy. For the mathematics of this theory to work, these strings must vibrate in more than the three spatial dimensions we experience. The theory requires extra dimensions, all curled up into shapes so minute we cannot detect them. Our familiar cosmos of length, width, and height could be just one of many dynamical brains existing within a vast, higher dimensional expanse called the bulk. In this radical picture, the particles that make up our atoms and light are not free to roam. They are like open strings with their endpoints glued to our home brain, which is why we are forever confined to these three dimensions. But gravity is different. It is carried by closed loops of string which are not tied down. This provides an elegant explanation for one of physics' deepest puzzles: why gravity is so astonishingly weak compared to the other fundamental forces. The gravitational force may be diluted because it is the only one that can leak or spread out into the full volume of the higher dimensional bulk. We only feel a faint shadow of its true strength, a tiny fraction that remains pinned to our brain. This framework, known as the Randall-Sundrum model, transforms our understanding of reality's architecture. It allows for astonishing cosmological scenarios, such as the cyclic model of the universe, where our brain periodically collides with a parallel brain in the bulk. Each collision would release cataclysmic energy, appearing to us as a new Big Bang, resetting the cosmic cycle for eternity. This hidden structure of brains and the bulk suggests that the cosmos is a far richer, more layered place than we ever imagined, a single page in a vast multidimensional book. But if these extra dimensions are real, what is their precise shape, and how does that shape determine the laws of our reality? The answer lies in the intricate geometry of spaces known as Kalabi-Yau Manifolds. The intricate shape of these hidden dimensions dictates the very laws of our reality. To reconcile the many extra dimensions demanded by string theory with our familiar four-dimensional experience, physicists propose that these additional spatial directions are curled up into vanishingly small, complex geometric forms known as Calabi-Yau manifolds. Named for mathematicians Eugenio Calabi, who conjectured their existence, and Xing-Tung Yau, who proved it, these shapes are the hidden architects of the particle world. In this framework, the fundamental strings are not just vibrating, they are vibrating in a space with a very specific compactified geometry. The different resonant patterns, the harmonics of a string as it moves through this convoluted landscape, directly correspond to the different particles we observe. One specific vibrational mode might produce an electron, while another creates a quark, and yet another manifests as a photon. The properties of these particles, their mass and charge, and how they interact with one another, are all determined by the exact topological shape of the Calabi-Yau manifold. It is as if the universe has a tiny, six-dimensional musical instrument at the heart of every point in space, and the notes it plays are the particles that make up our world. This profound connection suggests that the entire diverse zoo of subatomic particles and forces could be unified through geometry, a single elegant explanation for the complexity we see. The search for the one true Calabi-Yau shape that describes our universe is one of the great quests of theoretical physics. But if the geometry of space can dictate the laws of physics, could the universe itself be engaged in a cycle of cosmic rebirth, where geometry dictates not just the laws but the very timeline of existence? Roger Penrose envisions a cosmos without beginning or end, an infinite loop of cosmic death and rebirth known as conformal cyclic cosmology. In this breathtaking model, our universe is but one chapter, one eon in an eternal story. Each eon starts with its own hot Big Bang, expands for trillions of years until all matter decays and black holes evaporate, leaving behind a cold, empty universe of pure radiation. At this pivotal moment, the geometry of spacetime undergoes a profound transformation. Through a mathematical rescaling called a conformal transformation, the vast, endless future of one eon becomes mathematically identical to the hot, dense, low-entropy singularity of the next. The end of time seamlessly becomes a new beginning, resetting the cosmic clock in an infinite cycle. This hidden structure of conformal geometry allows the cosmos to forget its scale, making the infinitely large and the infinitely small equivalent. Evidence for this radical idea may be written in the sky. Penrose and his colleagues point to anomalous, circular patches of warmer temperature in the cosmic microwave background, which they call Hawking points. These, they propose, could be the imprints of the final, explosive evaporation of supermassive black holes from the previous eon, their last whispers etched onto the dawn of our own. This cyclical universe challenges the very idea of a singular creation, replacing it with an eternal, breathing rhythm of existence where every ending is merely a prelude to a new dawn. But if the universe itself is reborn, what role do the most destructive objects in creation, black holes, play in this cosmic cycle? Their event horizons are not ends, but gateways to an incredible hidden structure. This boundary of no return is a hidden membrane in the cosmos, a one-way street for reality. An event horizon is not a physical surface you could touch, but a mathematical boundary in space, a point of no escape where the black hole's gravity becomes so intense that not even light can fight its pull. According to Einstein's general relativity, this frontier should be a perfectly smooth and featureless curtain, a silent and simple gateway, but quantum mechanics paints a far more chaotic and dynamic picture. It suggests this horizon is a seething firewall of intense energy, or perhaps a complex, pixelated screen that stores information. This paradox was thrown into sharp relief by Stephen Hawking's revolutionary discovery. He realized that the intense quantum activity just outside the event horizon allows a black hole to slowly leak radiation, a faint glow we now call Hawking radiation. This process causes the black hole to gradually lose mass, evaporating over astronomical timescales. But here lies the crisis, the information paradox. The Hawking radiation appears to be completely random, carrying no data about the material that fell in. If the black hole vanishes, what happened to the information that described every star, planet, or person that crossed its horizon? Quantum mechanics insists that information can never be truly destroyed. So is it lost forever, or is it somehow preserved? The holographic principle offers a profound solution, suggesting that all the information about the infalling matter is not lost inside, but is perfectly encoded and stored on the two-dimensional surface of the event horizon itself. The three-dimensional interior we imagine is a projection from that data-rich surface. This makes the event horizon the ultimate cosmic hard drive and the most extreme laboratory for testing the laws of physics. It is a hidden structure where the two great pillars of modern science, relativity and quantum mechanics, collide, forcing us to rewrite our understanding of spacetime, information, and reality itself. Beyond this enigmatic boundary, the known laws of physics break down, leading to a place of infinite density, the final mystery waiting at the heart of the darkness. At the very heart of a black hole, where the event horizon gives way to the final descent, lies a boundary beyond our comprehension. This is the singularity, a hidden structure predicted by Einstein's equations where the curvature of spacetime becomes infinite and the known laws of physics simply cease to apply. It is a point of infinite density, a place where matter is crushed to a state beyond our understanding, and the very concepts of space and time lose their meaning. This is not just an extreme environment, it is a fundamental limit to our knowledge, a cosmic error message in the equations of general relativity. The existence of a singularity signals that our best theory of gravity is incomplete, that it cannot describe the universe's most violent moments, from the core of a collapsing star to the very first instant of the Big Bang. This challenge has forced physicists to propose radical alternatives. Theories like loop quantum gravity suggest there is no singularity at all, but rather a quantum bounce, a moment of supreme density where spacetime is repulsive, turning a catastrophic collapse into a new beginning. String theory envisions a fuzzy, non-geometric phase where the classical idea of a point breaks down entirely. These singularities, whether real or theoretical limits, act as cosmic signposts pointing toward the ultimate goal, a final theory of quantum gravity that can unveil the universe's true origins. How can we possibly observe the echoes of such hidden, cataclysmic events? The answer ripples through the fabric of spacetime itself. These faint ripples in spacetime are a collective hum from the universe's most violent events. We have now detected this gravitational wave background, a hidden structure of low-frequency vibrations that constantly wash through the cosmos, stretching and compressing the very fabric of reality as they pass. Predicted by Einstein over a century ago, these waves are generated by the orbital dance and cataclysmic mergers of supermassive black holes, each event sending a tremor through spacetime that travels for millions or even billions of years. Collaborations like NANOGrav recently captured this signal not by listening for sounds, but by using pulsars, the universe's most precise natural clocks. These rapidly spinning neutron stars emit beams of radio waves with metronomic regularity. By carefully monitoring an array of these cosmic lighthouses across our galaxy for over a decade, scientists detected a common, faint jitter in their rhythms, a telltale sign that spacetime itself was subtly flexing as these long wavelength gravitational waves passed through. This background is a cosmic symphony, with a combined rumble of countless black hole binaries creating a persistent bass note that underlies the entire universe. It also holds whispers from even more exotic sources, potentially including the snap of cosmic strings or the violent phase transitions of the young cosmos, events that left no other trace. This discovery gives us an entirely new sense, allowing us to hear the hidden structures of the cosmos and observe phenomena that light can never reveal. How do these vibrations and all the structures we have explored fit into the overall shape of space itself? The large-scale topology of the universe holds the final answer. This final hidden structure addresses the ultimate shape of reality itself, the large-scale topology of the universe. While we speak of an expanding cosmos, its overall geometry might be far more intricate than a simple, infinite flat sheet. The entirety of space could be finite and multiply connected, a concept where the fabric of the cosmos loops back on itself in a higher dimensional pattern. Imagine the surface of a donut, a torus. On this surface, a traveler moving forward in a straight line would eventually return to their starting point from the opposite direction. Now envision that principle applied not to a two-dimensional surface, but to our entire three-dimensional reality. We could be living within a giant, cosmic three-dimensional torus, where a powerful telescope pointed in one direction might, after looking across billions of light years, see the back of our own galaxy. This is not about a curved path through space, but a fundamental connectivity of space itself. Such a finite universe would act like a cosmic hall of mirrors, where the light from a single, brilliant quasar could travel along multiple, distinct global paths to reach us, creating ghost images of the same object scattered across the sky. The most promising place to find evidence for this is in the oldest light we can see, the cosmic microwave background. If the universe is small enough, these primordial ripples would wrap around the cosmos and overlap with themselves, creating specific, telltale circles or correlated patterns in the temperature map, a subtle fingerprint of the universe's hidden connectedness. This topology is deeply entwined with the universe's geometry and its ultimate fate. A finite, multiply-connected universe would have profound implications for whether the cosmos is open and will expand forever, or is closed and destined for eventual recollapse in a big crunch. The search for this structure pushes cosmology to its absolute limits, asking if the vast expanse we observe is truly infinite, or a beautifully finite and intricately woven manifold, a cosmic kaleidoscope with hidden connections defining its every contour. Having journeyed through these 25 hidden structures, from the quantum foam beneath our feet to THE, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter of the cosmos, a profound pattern emerges. Each layer, from the Higgs field granting mass to the holographic principle encoding reality, reveals a universe built not on chaos, but on an intricate, deeply hidden architecture. These are not just abstract ideas, they are the fundamental scaffolds of existence, the invisible gears and pulleys behind everything we see and are. They teach us that reality has a deep and elegant order, a coherence that binds the quantum to the cosmic. This journey through the fabric of the universe reveals that the greatest mysteries are not always the most distant, but are woven into the very nature of space, time, and existence itself, waiting just beyond the veil of our perception. This intricate cosmic architecture is not a collection of separate blueprints, but a single, deeply unified design. Each hidden structure we have explored, from the frothing quantum foam to the vast gravitational wells of dark matter, is a vital thread in one magnificent tapestry. The Higgs field gives substance to the particles that dance upon the quantum stage, while the strong nuclear force binds them into the atoms that build our world. The principles of Lorentz symmetry and quantum entanglement weave a fabric of reliable laws and invisible connections, ensuring the cosmos operates as a coherent whole rather than a collection of disjointed parts. This interconnectedness means that the geometry of a Calabi-Yau manifold, curled up in extra dimensions, directly influences the particles we see, and that the faint whispers of primordial sound waves, frozen in the cosmic microwave background, dictated the location of every galaxy, including our own Milky Way. The holographic principle suggests that even this grand, three-dimensional reality might be a projection from a simpler, two-dimensional surface, a final, breathtaking unification of information and existence. This is not a universe of random chance, but one of deep, elegant order, governed by mathematical beauty and geometric principles that have been at work since the first instant of time. So how does this profound understanding touch our everyday lives as we navigate a world of work and family and simple routines? The realization that we are part of such a coherent, magnificent system can transform our perspective. It invites us to see the hidden elegance in the world around us, to recognize that the stability of the chair you sit on, the light from your screen, and the very atoms of your body are all gifts from these unseen cosmic frameworks. This knowledge fosters a sense of wonder that is accessible to everyone, a reminder that curiosity about the universe is not reserved for physicists in laboratories, but is a fundamental part of the human experience. It encourages us to look up at the night sky not as a distant void, but as a living, structured cosmos of which we are an intimate and inseparable part. Yet beneath this intricate cosmic architecture lies a simple, profound truth. We have journeyed through 25 hidden structures, from the gravitational wells that guide galaxies to the quantum entanglement that instantly links particles across the void. Each layer reveals a universe built not on chaos, but on a deep, elegant order. These frameworks are the invisible gears and pulleys behind everything we see and are, granting mass to particles through the Higgs field, forging atoms with a strong nuclear force, and encoding reality itself on a two-dimensional boundary according to the holographic principle. This interconnected tapestry means the geometry of a Calabi-Yau manifold dictates the laws of physics, while the faint echoes of primordial sound waves set the location of every star. So what does this mean for you right now? It means the stability of the chair you sit on, the light from your screen, and the very atoms of your body are all gifts from these unseen cosmic scaffolds. This knowledge transforms our perspective, inviting us to see the hidden elegance in our everyday world and recognize our intimate part in a magnificent, structured cosmos. It fuels our greatest technological leaps, from quantum computers to deep space exploration, and reshapes our deepest philosophical questions about existence and our place within it. As Carl Sagan once inspired us, somewhere, something incredible is waiting to be known. Let this exploration be your starting point. We would love to hear which hidden structure fascinated you most, so share your thoughts in the comments below. Subscribe for more journeys into the universe's deepest secrets, and always remember to look up. The cosmos is a story still being written, and you are here to read its pages.